Let's talk a bit about asymptotes. Asymptotes describe behaviour of the curve. Now here's a random curve I drew up trying to get as many different types of asymptotes that I could in there. So the different types. Vertical asymptotes, there's one there. Now vertical asymptotes, they tell us what happens at the extremities of the y values. So in other words, as x approaches a particular value, the function or the y value is going to either plus or minus infinity, and in this case our function is going to both. On the left hand side it's going up to positive infinity, the right hand side it's going down to negative infinity. Now functions will never ever touch or cut a vertical asymptote, because a vertical asymptote is an exclusion in the domain. It's not in the domain, there can't be a y value there. Then we have horizontal ones. There's one there. Now that's also the extremities, but this time it's the extremities of the x value. And so it's when the x value is going to plus or minus infinity, what is the y value doing? Now, on this example, out at plus infinity, we're going to this horizontal asymptote of b. Out at negative infinity, it's not going to a horizontal asymptote. It's going to an oblique asymptote, so one that's at an angle. And that's when both of the x and the y values are going off to the extremities. In this case, as the x value is going off to negative infinity, the y value is going off to positive infinity. It is okay for curves to cut horizontal or oblique ones, and in this example I've got it cutting in fact both of them. It can do that. That brings us to our next basic type of function, that being the hyperbola, but in this case I'm talking about the specific one of the rectangular hyperbolic function, which is the one we're used to seeing for y equals 1 on x, or another way of seeing that is x times y equals 1. A hyperbola, or something like this, that's inverse variation, because we'll see that as the x value gets bigger, the y value gets smaller, and vice versa. So it's inverse variation. The reason it's called the rectangular hyperbola is because the two asymptotes are at right angles together. So that's why we call it a rectangular hyperbola. All rectangular hyperbolas can be transformed from this basic one using the different transformations or dilations. How do we recognize it? Here's our basic one. I guess the key is that one of the variables is in the denominator. I suppose theoretically both of the variables could be in the denominator, but as soon as you see one of those variables in the denominator, that curve is probably going to have some sort of hyperbolic nature to it. The other type of curve that we see a lot that has asymptotes is our exponential function. And the way we orient the exponential function all has to do with the actual base. The one I've drawn here, y equals a to the power of x, the base is bigger than 1. It will start very shallow and then it will increase and get rapid very quickly. If the base was less than 1, then it would flip and go the other way. It starts off steep and then becomes shallow. Well, when I say less than 1, of course that base is in between 0 and 1. We don't really have negative numbers as an exponential, because if we were to draw, I don't know, let's say negative 2 all to the power of x, you're not going to get a curve. You get a series of random points, because you can't, for instance, say negative 2 to the power of a half, because you can't find the square root of a negative number. So that would be an exclusion in the domain. Whereas a third's okay, you can find the cube root of a negative number, so really it's a very chaotic sort of thing. So we don't normally talk about exponentials with a negative base. I suppose you could have a base of power of 1, very boring curve. Do you call that an exponential? Think about it. 1 to the power of x, what's it going to be? Yes, it's going to be the horizontal line, isn't it? Because 1 to the power of anything is 1. So is that an exponential or is it a linear function? So we don't normally deal with that one. And of course, 0 to the power of x, what would that look like? Well, you could draw it, but what would it look like? If for some reason we wanted to draw 0 to the power of x, well, what sort of problems are we going to have with that? 0, we know 0 can't be on the bottom of the fraction. So what can't that power be? Negative. So therefore we know there's no negative numbers in the domain. If it had a positive power, what would 0 to the power of x be? Maybe I'll ask an easier question. What's 0 squared? What's 0 cubed? 0. What's 0 to the power of 5? Oh, I'll get a trickier one. What's 0 to the power of a half? Okay, so what are we going to get if x is a positive number? 0. What about 0 to the power of 0? Does it exist or doesn't exist? Might be a point discontinuity there, so we're saying, hey, that's where it stops. Unless you think 0 to the power of 0 is 1, then it would jump up to 1. Or is 0 to the power of 0 0, then I'd colour the dot in. Hence, nothing we look at there looks like an exponential, so we don't really call it an exponential. How do you recognise it? Pretty easy to recognise. One of those pronumerals is going to be in the power, because of course another name for the power, well, is index, but yet another one is exponent, hence the name of the curve, exponential. So the base is positive, not equal to 1. There we go.